this will be homework 4 part A. In this we're going to find the differential equations for the heights of each of these tanks that will be in succession. So there will be flowing in from up here, and it will flow out this hole, then this one will flow into this, and then this will flow into the atmosphere. And we will find the differential equation for the heights of these tanks based on the flow coming in. So the first thing we're going to do is kind of think of these tanks as a system of mass, and that mass is going to be constantly changing. So our change in mass, or our mass in this case, would be our density times our volume. That would be changing with time, will be equal to our density in times our flow in minus our density going out times our flow going out. And assuming we have an incompressible liquid, we can know that our density will be the same at all stages because it is an incompressible liquid. So we can get rid of our density part of all these equations. The next thing we need to do is think of our volume in a different way, and our volume can be calculated by our cross-sectional area times the height of the tank. So we can have our change in cross-sectional area times height over our change in time is equal to our Q in minus our Q out. And in this situation, our Q out would be equal to the area of this hole, or we'll call it AD, times the velocity at which it's flowing out. And to calculate this velocity, we can use Bernoulli's equation and the idea of energy conservation to represent our V as the square root of 2GH. It'll make it easier if we have our H on the outside later on. So we can replace our V with the square root of 2G times H to the 1/2. Now that we have this, we can fairly simply solve for just a differential equation for our change in height by dividing by AC. So we'll divide this by AC and take this out for now. That we have our general equation for how to find the changing height of the tank, we can put this in terms of each tank. So I'll start with the first one, which will just be our dH1 dt will be equal to our Qn in this situation would still be our Qn minus what's going out, so AD1, but they're all the same, so that doesn't matter too much, times our 2G H to the 1/2. That's all over AC. Our second one, second tank, dt, be equal to this, so AD1 times 2G H to the 1/2 minus what's going out, so our AD2, even though in this case they would be the same, times 2G H to the 1/2. That's over AC as well. That's AC1, AC2. And then we can do our third tank, which dH3 dt is equal to our second rate going out, which would be going into the third. So AD3, again, the same times, this needs to be H1, this is H2, it's H1. Okay, and 2G times H2 to the 1/2 minus Oh, that's 2 again. Minus what's going out of the third tank, so AD3 times 2G H to the 1/2 over the cross-sectional area of tank 3. And those would be the differential equations for the changing heights of each tank. And one more important thing that we should do is figure out the initial height from this information, which will be very useful for when we code this. So at the initial height, our change would be 0. So we get 0, and then we will split these up, or I guess not split them up, but make the AC separate over AC1. And then we'll move this to the other side of the equation. So we get AD1 times 2G H to the 1/2 over AC1 is equal to QN over AC1. We can cancel these out and divide by 81 times square root of 2G gives us H to the 1/2 is equal to our QN over AD1 times 2G. And if we square this, we end up with H1 initial is equal to QN squared over AD1 squared times 2 times G. And because it's at the initial steady state, our QN for all of these will be equivalent. And since our AD is the same for each tank, that will also be equivalent, meaning this would be the initial height for each tank. All right. This is going to be homework for part A2, in which we'll use the equations we just derived to sort of simulate the levels at which the tank would be at by changing the initial flow rate to 0.15 instead of 0.1. And then we have our drainage hole given and the cross-sectional area of each tank, 1, 0.5, and 2. So I've imported NumPy, SciPy, integrate, solve IVP, which we'll use to solve this problem, and our plotly subplots in order to plot our results. And some of the givens, our gravitational constant, our initial flow rate of 0.1, what it will change to when we start. So 0.1 times 1.5 is 0.15. Our cross-sectional area of tank 1, 2, and 3. The area of our drainage hole, which is 0.01 for all of them as an array, and the time at which we will end. So the first thing we'll need to do is get our initial height, because solve IVP requires an initial height to do what it needs to do. And that was the last thing that we derived in the first part. So our H0 is going to be equal to our QN0 squared divided by our AD squared times 2 times G. And that should get us our H0. So we'll enter that. And then we'll need to make a function that will represent our dH/dt. So we'll define our dH/dt as a function of time and the height. And the first thing we'll need is our Q1, our Q2. And these can be gotten by using the equations we derived for dH/dt. So it will be equal to our AD times 2 times G times H, and that will be the square root of that. Just make sure all this is grouped together. All right, and then we'll want this to return our dH/dt. So using our Q1 and Q2s, we can get these So we'll start off with our first tank, which coming in will be our regular Q in minus Q1, which would be going out. Let's make sure these stay together. And then this will be divided by our cross-sectional area of tank 1. Our next change in height will be represented as our Q1, which would be the liquid coming in, Q1 minus Q2, which is what's going out. And this will be divided by the cross-sectional area of tank 2. And lastly, we will have our Q2 minus our Q3 going out. And this will be divided by the cross-sectional area of tank 3. So now that we have our equation, we can finally use solve IVP. So our results will be equal to solve IVP of our function dh dt from 0 to our t end. And our initial value will be h0. We want our dense output equal to true, so that way we can pull our specific values later on. And we'll need a range for which this can be plotted on, so our t plot will be equal to np in space from 0 to our t end, and we'll say we want 500 points. Now, to get our h values at each of these points, h1, h2, and h3, will be equal to res.sol of our t-plot values. So now we can begin to make our scatter plot. So fig equals make underscore subplots. And we can fig dot add scatter. We can do x is going to be equal to t plot. Our y will be equal to h1. Our name will be h1, and the mode for this will be lines. And this should be the same for pretty much all of them. So just change this down and change out the numbers where they need to be changed. 3, 2, 3. And if we put this, we can see that changing our initial flow rate to 50% more, or 0.15, would change our initial steady state of around 5.1 and bring all of them up to around 11, the green one being the lowest, and our red and blue coming to about the same point at 11.4. And that's going to be part A2.